We're continuing our section on relativity, the special theory of relativity, and we have just completed section 37.5, but there were two equations that I did not cover because they were on this next page that I thought I would mention here. One of these shows I'd already done the ch squared minus sh squared, and I compared it to the cosine squared minus plus the sine squared, the n1. Here we have a negative sign for the hyperbolic functions. Here we have a positive sign for the regular trigonometric functions. And if you actually compute what psi is, and then the ch psi, you find that ch psi is equal to 1 over the square root of 1 minus v squared over c squared. And that sh psi is v over c over the square root of 1 minus v squared over c squared. Therefore, it's very easy to check that the square of this minus the square of this is exactly equal to 1. And you can see that because you get 1 minus v squared over c squared, and the denominator, when it's squared, becomes 1 minus v squared over c squared in both places. And so you get a 1 divided by 1, and sure enough, that is 1. So I just thought I would mention that. Now, what we're doing now is beginning with chapter 30, module 37.6, the relativistic scalar product. Kind of like the last section, this relativistic scalar product is a little bit advanced for the 201-202 algebra trig level. I thought I would mention it here because it's used, some of these ideas are used in general relativity, and I just want to kind of set the stage. None of this normally would be on the test in a 201 and 202, but some of it may be on a test in a more advanced, like the calculus level engineering and physics material, for which this course also can, these lectures also double. I want to talk about the scalar product. You're familiar with the scalar product, like a vector A dotted with a vector B, and that is a vector A will have components AX, AY, and AZ as an ordered triplet of numbers, or better yet, we could write them as A1, A2, and A3. This is better than using the X, Y, and Z, but we know that these are the X, Y, and Z components. And if I take the dot product of that with the B1, B2, B3, then this dot product is equal to A1 times B1 plus A2 times B2 plus A3 times B3. And it is invariant. And this is equal to the length of A times the length of B times the cosine of the angle between A and B. Any vector space that has a dot product defined on it is therefore called a metric space, meaning we can get the length of vectors and the angle between vectors. If I take A dot A, then you can see that I get A1 squared plus A2 squared plus A3 squared, which is exactly like AX squared, AY squared, and AZ squared, or X squared, Y squared, and Z squared. So therefore, the length of a vector A is, this is A times A, so it's the length squared. So this becomes, because the cosine of between a vector and itself is 0, so it's, this cosine is 1. So A is the square root of A1 squared plus A2 squared plus A3 squared. And that gives us the length of a vector, and this is the Pythagorean theorem. So the Pythagorean theorem is contained in the scalar product. Okay, that's fine. Well, what is the scalar product in relativity? It's really quite different. You have here 4 dimensions, so a vector like x would be equal to x0, x1, x2, and x3. But the scalar product has what is called a metric in it. And this metric, G, has this has all the off-diagonal elements equal to 0. So this G, mu nu, mu and nu go 0, 1, 2, 3, is equal to a matrix that looks like plus 1, minus 1, minus 1, minus 1, with zeros off the diagonal. And so when it multiplies two vectors and sums them up, it gives us an x times a y as a scalar product is equal to g mu nu, x mu, y nu. Mu and nu are now summed over all values from 0 to 4. And this gives us, because I only get diagonal terms, x naught, y naught, minus x1, y1, minus x2, y2, minus x3, y3. And for a vector with itself, this becomes, if these were both x's, this would become x dot x in 4 dimensions would be c squared t squared minus x squared minus y squared minus z squared, or equivalently c squared t squared minus r vector squared. And that's the length of a vector, and this is invariant. The dot product is invariant under the transformations that describe that space, and just as the regular dot product is invariant under rotations, which is the Pythagorean theorem, this dot product is invariant under the Lorentz transformations. And so we can write this amount, if it's infinitesimal, as d tau squared g dx mu dx nu, and that will be invariant, and that d tau squared is c squared t squared minus dr squared, which is the infinitesimal version of this. And this d tau gives us the number that sits on a clock while it's moving. And the reason for that is you can see that if the observer sits on the object, dr never changes, and so d tau is equal to c dt. And this d tau is called the proper time. And it's a very important concept in special relativity. We can use that proper time rather than regular time to take derivatives of vectors. So we define what is called our velocity. Our velocity would be v mu, meaning it has 4 components, and it would be dx mu over d tau. And this is velocity in relativity. And if I look at the length of this, it turns out that this length is equal to c squared t squared minus dx squared, and so it's actually equal to 1. So we need, since this is dimensionless, we need a value here like c to give it a speed that's comparable to meters per second. And so when we do that, this becomes something that has a length where v mu times v mu is equal to c squared and is invariant. Then we can define momentum, p mu, to be the mass of an object times its velocity. So this defines our momentum, this defines our velocity, and the momentum does give us this p mu, and when we work this out with p naught and p vector, it becomes, we find that p naught is equal to the energy divided by c, and that x naught is equal to c times the time. So time and energy become like the 4th dimension for position and momentum. I understand that these are hard concepts. This is just an overview to give someone kind of a glimpse into the further depth of relativity and its special theory. And so if I take this and I look at this scalar product, it becomes e squared over c squared minus p squared is equal to m squared c squared. And the m comes from this m, the c comes from this c, and it becomes m times c times squared. And then the other components become the p naught squared. And so those are the same things. And that's very elucidating and tells us a little bit more about how we deal with velocity and momentum and energy in 4 dimensions.